Yeah, I can get started. Can you hear me?
Yes.
Okay, great. So let me share my screen. You can see my screen, right?
Yes.
Okay, so I'll just go over questions 1 and 2 in the homework. So I don't think it will take the full time, so probably will take 1 hour, but we can have more discussions. I was able to solve question 1 by myself, but question 2 I was not able to. But we can discuss the solution, reference solution, and how they deal with it. I haven't looked at question number 3, but we can leave it for next week. And then the collab notebooks, where did it go? Well, maybe I didn't open it. The collab notebooks are basically the homeworks, and then one or two extra other interesting things that we can also do next week. Okay, does that sound good?
Yep.
Okay. So in question number 1, this is the warm-up. This is the only one I solved. So yeah, I feel I had the confidence to start actually solving these myself. But let's stuck on to question number 2, and I can discuss more about all the different problems and things that I encountered. So here's question number 1. So we have this data set, 1D data set. So visualize 1D data set is will show us this. So if we look at the data itself, so if we I can do the test. Yeah, this is the question 1, part A. 1A. So this is just oh, it says right here 20,000 by 1, and so the plot is actually the plot of the histogram, and you can see the train data is 20,000 to 1 by 1. So this is a plot of the histogram. So the goal here is all we have to do is we'll train our generator and discriminator via the original GAN minimax objective. So use an MLP for both your generator and your discriminator, and train until the generator distribution resembles the target distribution. Okay, so so here we have to create a generator and a discriminator based on an MLP. And then we'll train until the distribution resembles the target distribution. So here's my solution. So it's not the it's not perfect, but we can look at the reference solution. So here's the discriminator I made. So all it is just it does. Okay, so let's go first with the generator. It starts with 4. That's a latent latent variable space. So I assume that maybe 4, because you could think of it as 2 means and 2 sigmas, right? So this is 2, but there is no notion of there isn't any normal distribution. So hopefully you can learn these shapes, but then we just have 4 latent variables, and hopefully you will learn something like a mean and 2 means and 2 standard deviations. It goes into 100, and then we do ReLU, goes into 100, and then we go down to 10, and then it goes to 10, and then it goes to 1. So we need 1, right? Because we're generating numbers. So it just has to generate a number. Okay, and so on the discriminator side, we take a number and then it has to say, it has to, from a sigmoid, it has to say, is this a real data point or is this a fake data point? right? So that's like the simple idea. And I only did 2 layers, so I think that's maybe should be fine. Okay, so that's the generator and the discriminator, just basic neural networks, basic MLPs. And so this is the training loop. So there's a lot of these things that are needed for the returning the values. So there's you have to return like 8 or 10 different things. But let's just if we just go over it. So the algorithm is basically this algorithm right here, the GAN pseudocode, and it's I think I tried to make it exactly the same as this one. Okay, so and I know it says you have to stop when it becomes close enough, but I just put num epochs and then instead of actually stopping at a threshold or something like that. Okay, so the idea is to create the generator and the discriminator, the models, right? And these are for the return value. So and then this is our standard data loader, so that our training data can be broken down into batches and stuff like that. And then we have the optimizer for the generator, optimizer Z, and then optimizer D for the discriminator. Okay, so that's pretty much standard stuff. And so this is the algorithm exactly. So we, okay, I'm gonna switch. So we have to do a number of training iterations. So that's the number of epochs for K steps. And then, and K steps is the number of times to train the discriminator. And yeah, okay, so the batch size and the epochs are kind of in there. So there's 2 for loops, but we have 3 because we have the epochs and then we have the going over the training data sample. But you can think of yeah, epochs as one step over. So for in this loop, so we can see what they do. So we sample a mini batch of noise samples, sample a mini batch of actual data, and they say update the discriminator by ascending a stochastic descent. Okay, so going back. So this is the sample, sorry, the random values in the latent space from Z. So it's just a random a batch size. Yeah, this probably should be the size of the batch here, but I changed it so that the last batch is the same size. All the batches are the same size, and then latent size, which is 4 for us. And then we take this and then we push it through model G, which is the generator. So we get the GZ, and then we push the ZZ through the discriminator, and then we get DGZ. And right, so DGZ is this part, DGZ. That's the, we generate the data, we get the random latent space, we get it to the generator, and we get it to the discriminator. And then the next one is the DX, where we discriminate the actual model. So this is the DX part. Okay, and then so we calculate the loss, which is just basically the DX plus 1 minus DGZ, right? So this is the yeah, and then and this is just to print out the progress, and then we just do the optimizer step. We do the backward step. So that's the discriminator training part, and then so we have the loop slightly out, one loop outside. So once the K steps are done, so sample a mini batch of noise samples, and then update the generator. And this part. So again, we make the noise sample, we put it through the generator, put it through the discriminator, and then we calculate the loss, right? So 1 minus dc, 1 minus dgc, and then we update the we update the optimizer, but this is the generator optimizer. The previous one was the discriminator optimizer. And this is, oh yeah, if we have to make some epoch 0 samples, so that one of the requirements of the homework is that you create a sample from epoch 0. And then you take the samples at the end of the training. So this is epoch 0 samples, and then see how you did at the end of the training, and you return everything else, right? So pretty standard GANs stuff. So I can continue on. Which one is continue? Resume program. And is it running? Yep. Sometimes it converges, sometimes it doesn't. So this time it didn't converge. So let me try again. So this time it failed, but let me just run it so that it's running in the background. And so the error does seem to go down, but what it generated was it put all of the fake distribution in one point. So it failed. Yeah, it failed. So this is my second run. So it has a weird loss where it's actually increasing. So, oh, where was it? Sorry. This is for iteration 0, and this is after an iteration. It didn't change. So the first run was like really, really bad. So the second run, this was the first starting point. So I think it gave us some more random starting point. And then after training, it took this shape, but it put too much emphasis on this one. So I can run it again with more. I don't know what the. It's just that I run it 3-4 times. One time it gives a good answer, and then other times, the other time it gives a bad answer. So it's probably some randomization, starting randomization of the weights or something like that. Like this time it's a little bit better, right? So so this was the where is this? So this was the first, because you can see the starting point is different. Like this was the first one. It just generated this one, random numbers first, and then after training, it got to this point. So so the starting values really affect it. So if you have a bad starting point, then I thought about putting a seed and then using the seed to randomize it so that I always have a good one, but I didn't do that. So okay. Any questions on those?
What is a green line stand for?
This one, the green one? Oh, I think this is just like the decision boundary. So what you do is you take a lin space. I should have explained. Lin space is equally spaced line between negative and 1 and 1 of 1000, and then you pass it through. Pass it through the discriminator, like the lin space, and it says, okay, how does it classify each of these points? So as here it's not sure, and then if I give you something, if I give something like 0.25, then it knows it's fake. If I give something over here, then it knows it's fake. because there's not many points here, but it basically shows how fake it thinks across the number line from -1 to 1. Does that make sense?
Oh, yeah. So here, so in this case, the discriminator is kind of unsure in most cases, right? So there is only this kind of.
Yeah, I think maybe it's because the scale is from 0 to 1. So yeah, it is like squished down here, but I think here it's pretty sure that it's fake.
Okay, but still, it's kind of most of the time it's around 1/2, right?
Yep. And I can show where is it? The starting point. Where did you go? This is the starting point. Maybe here it's like, yeah. It was very bad, right? So here it thinks it's fake, and then it thinks it's real here. So it improved. I guess the point is that it improved.
Okay, sure. So the discriminator is kind of suppose so this decision boundary or like a probability of being real or fake. Ideally, it should be of the same shape as the histogram, right?
Yeah. If
scale between 0 and 1.
Yeah.
All right.
Yep. But yeah, it's not based on what the generator produces, but it's based on a linear space. So I mean, ideally, like if we say it should be 0.5, but then this is just generating each of the numbers between -1 and 1, but not actually asking the generator to make the points. So it's a little bit different, right? So but yeah, I could have experimented with more latent variables. Anyway, it's fine. It's so so let's go to part. Any other questions, or can I go to part B?
Go ahead.
Okay, so let's go to part B. So we'll use the so part B it's a very small change. So we'll use the non-saturating formulation of the GAN objectives. Now we have two separate losses. So the discriminator loss is this, and generator loss is this one. Like the first part is exactly the same. So first part is exactly the same. It's just the second part, instead of 1 minus D, is just negative of the discriminator loss. Okay, so 1B. And so everything is exactly the same, except I changed this. So I can just run it. It's probably going to be the same thing. Oh, similar here. I improved the output here. Yeah, this is running on CPU, so I didn't do it on GPU yet. Oh, did I not do the first one? I don't know what happened to the first one, but this one actually does a better job, I guess. Or maybe we just got lucky here. I can run it one more time, see what. But this is supposed to be the. I don't know what happened to it. Something it's like all concentrated on one value, maybe. All the samples are all 0. Yeah, so sometimes it also has the same problem. There's too many samples on this one. So it was here, it had to move everything around. So it didn't quite get there in the time allotted, maybe more time than it would have worked. But yeah, I maybe should put a seed so that, I know which one are the good starting points and randomize it properly. But okay. Any questions on this one?
Yeah, I've
Yeah,
got
Sure. Sure, go ahead, please.
a question about this. So here about your code here. So
Yeah.
we sample a batch in the second for loop. So we have a first for loop for the epochs.
Yeah.
Then we have a loop over the data loader.
Mm-hmm.
And then we have another loop for like how many steps we want to train discriminator between the updates to generator, right?
Yeah.
And shouldn't we sample a new batch for each of the discriminator updates?
Probably. I think the discriminator is k = 5. Yeah, on the actual algorithm, they don't do that. So yeah, it's the same over the same, or I guess it's sample a different different one. Probably, yeah. Maybe it's an error on that part.
Yeah, I don't think like it will make a big difference, but still it might be kind of making this problem with mode collapse or something a bit worse if you do multiple steps with the same mini batch. Yeah. Okay.
I agree. I thought about it, but I didn't change it.
Do they do that in the reference? Do you know?
Okay, yeah, that's the next thing we can do is go to the reference one.
Before we go there,
Okay.
one other question I had is the I was just wondering, the second loss that you used is the non-saturating loss, right? But don't have the equations in front of me, but is it similar, or is the hinge loss something yet again different? And if you were to use the hinge loss, would that be something different? Remember, I think in the second part of the first lecture or something, he introduces, or one of the variants, I forget whether it was big GAN or style GAN or the spectral norm GAN, or one of those begins to use hinge loss for the loss versus regular generator discriminator adversarial loss. So I was just wondering whether, and I don't recall, this looks, this part 1b looks somewhat like the hinge loss. So is the non-saturating loss the same as, and I just don't recall the equation.
I forgot what the hinge loss is. Let me see if I can find it. But hinge loss, it's some sort of spectral normalization part.
It was either in spectral norm, or let me see my notes.
So I think this is still in the so all I remember is that the game theory part where it's adversarial. The first one is adversarial because one is trying to defeat the other. The second one is not adversarial, so it's not game theoretic, but it's essentially the same underlying objective. I think that's what's going on. It's like they're both KL divergence based, and then these spectral norms are all Jensen's Shannon inequality.
Yeah, the second one tends to give you the overlap between, where they say, oh, the first one, there's a step loss. So, especially in the beginning, when your generator does a poor job, then the discriminator is very sure. So it doesn't give you good gradients for the generator. And that's what you're trying to fix by creating some overlap and therefore using, the second part 1b loss, whatever the term for it is. And that begins to kind of bring the two distributions closer together so that there is some overlap to generate a good gradient for the generator from the discriminator when the generator is doing a poor job. That's the way I recall it.
Okay, yeah, that sounds somewhat familiar. There's this one, right? So yeah, this one.
Right, exactly.
Something like that.
So that helps for conversion, because when the generator is doing a poor job, which is usually the case in the beginning, then you get a good gradient if the two distributions overlap. If they don't, you get you pretty much don't get a gradient for the generator, which doesn't help the generator improve, and then there's not much that you can do. That's the way I remember the part 1B loss. But what I was trying to think through is if there's yet another variant that one of the future methods introduces. Yeah, I think in geometric GAN, they talk about kind of the hinge loss.
Okay.
It's different from part 1B. So that may be something, I'm again just thinking aloud loud, but that may be something else to try as part 1C, which is, change the, and by the way, in that also it looks like the generator loss remains the same. It's just the discriminator loss that's changed to a hinge loss.
Okay.
So that might be something else to try as part 1C.
Okay. I think this is, maybe it's the non-saturating formula. Yeah, this is the non-saturating formulation. Okay. Yeah, I remember this part. Yeah, it changed the. Yeah, you're right. Yeah, but this one, part 1 and B is just the standard one, and then the non-saturating formulation.
Non-saturating, yeah, and there is yet another one. It's apparently in the slides. If you search for geometric GAN, then you'll probably find the loss that I'm talking about, and that, I mean, just as something to try in the 1D because it's simple, is probably try a hinge loss as well.
Okay, that sounds good. I'll try that out. Okay, and so let's look at the reference. So, can we go to the reference solution?
Yeah. Right.
This is collab. Sorry. No, homework for solutions. I looked at it, and it is a bit more. It's different than what I did. So let me see where it is.
Yeah, I was curious whether they do what Atto was referring to in resample.
So I looked at high level. So one of the things that this is part A, part B, or what's going on? Part A. So one of the things is that they actually, I believe they do. So this is just the MLP class that they have before. So you give it the input size, number of hidden, and the hidden size, and it builds. It goes around and builds the whole thing. Oh, it's a leaky ReLU. I don't know why. I just use ReLU. And so one of the So that's what the MLP does. Just the standard MLP. And so here in this case, they have the latent dimension, and it's the same thing. It's the MLP self.MLP. The generator is also MLP. And then forward is just that they add the tan edge here. Oh wait, do they? Okay, I think this is just error. So this one is not called. So they just tan edge part is called. So in my case, I think I just it's a bit. Mine was kind of naive, where I just put everything in there. So tan edge. Or did I put tan edge? I guess I didn't bother with the tan edge. I could have put a tan edge in. Yeah, they have a tan edge here. And when you sample it, the sampling part is also inside instead of in the training loop, right? So the PTU is the PyTorch utilities that they made. So this is just it becomes the RAND. Okay, so this is I think similar, and then the discriminator is also similar, but then you have sigmoid at the end. So it's just MLP, wrapped in a sigmoid, and then I think they have the leaky ReLU here. And then, yeah, and I think they use this one. I didn't know about this one. So there's a scheduler so that you can train it until it reaches some satisfactory, or it changes the, I think this Lambda LR means that it changes the learning rate based on a function you give.
Yeah, it probably ends up reducing it after some time. So you
Okay.
converge faster.
And yeah, okay. And then what is this one here? Train and train epoch. So you have the optimizers. There's the G and the C optimizers, generator and critic optimizers, and then the LR scheduler. Not, I think it's turned off, and you just go over and then you call train. Okay, let's see. If for each epoch you have the generator.train, critic.train, and then inside there's a train. And then in the train loader, you do the critic, so which is the discriminator. And then if n critic is equals 0, so after so many, yeah, so they're doing it like how Arto suggested, is that you run it, the critic part. So in my case, it would be the generator part, right? So you run the where did you go? Yeah, the discriminator part, the critic part, n times. So yeah, that's a good trick, is that instead of having a for loop here, you just put everything aside and you say, well, only if the enumerate batch number is mod the discriminator k equals 0, then run this one. So then that, yeah, then that solves the problem. That's a nice trick, right? So if I mod n critic is 0, so every n critics step you do the generator, but then every step you do the critic. Right? Does that make sense?
Yeah. So that they did do what I was saying, which is like you were explaining, mod. So you run the discriminator for some steps, and modulo some steps, you run the generator, and then go back to running the discriminator modulo.
Yep. I think this is a nice. I didn't think about it. I was thinking like, how do I? It's going to be messy if I have like move the loops around. So I just didn't do it, but probably would be better this way.
Yeah. The one other thing I noticed is they seem to be doing some weight clipping.
Oh, I think it's set to none. I think it's
like
really? It would be good for part C. I think that's the weight clipping would, as you said, would do part C. It would be very simple. I think weight clipping is false here somewhere.
It was for enforcing lipschitzness on the function as it was mentioned. So that's for Wasserstein-Gahn, the first paper on Wasserstein-Gahn enforced Lipschitzness. Yeah, it's hard to say it correct. So basically, when you do this Wasserstein-Gahn, you need to clip the weights.
Yep.
Yeah, that's right. But what Morten is saying, it seems is that at least for this, they don't seem to do it for the simple 1D case. Is that what you're saying, Morten?
Yeah, it's weight clipping. Oh wait, where is weight clipping is used? Chain args.get.
They pass it in none.
Yeah, okay, it's default as none, I guess. Whenever they call train args is it's there's a lot of stuff going on train args, and then the train epochs is called, and then I think without a train epochs, train epochs critic, so it doesn't have the gradient clipping here. So I think it's set to false by default. So that's why. Yeah.
Okay, but as I was saying, maybe when they just set it up so they could use the same thing in the future. And
yeah. So yeah, it's set. Some of these things are set up so you can. It's more like flexible. I think all this stuff to use, but it's got more stuff in it. It's a little bit harder to follow, but yeah, it's pretty straightforward, I think. Yeah. But yeah, I didn't use the scheduler to update the steps. Yeah, this is the first time I see this. I've seen the scheduler. So my PyTorch skill is not. It's improving, but it's not. But it's good to learn about it. Okay. Any more questions, or can I go to question number 2? Okay, I'll go to question number 2. Okay, this one I basically don't have. I don't have the full skills to make it work, but I can just discuss it. What I felt was the problems, and maybe how they solved it, and how I couldn't figure out what were the problems. Okay. So question 2 is GANs on Cfr10. Cfr10 is image sample, and I think it's part of a package, data package. So they just download the whole thing if you run it on your local computer, and then it produces this image. Oh, I forgot one thing. I forgot the results that they had. Oh, I forgot this results. Sorry, I'm going back again. Okay, yeah, the picture. So their picture is, this is the result they had. But I'm very surprised that even in the first step, they have a pretty good results already. And it's probably because, yeah, they're using more of the data. And so in my first step, it's pretty bad, right? And then in the final steps, it's already very good. Yeah, just in the first, it's already starting to approximate. And
yeah,
then,
and do they see as much of a difference between the first and the second?
oh, this is the first and the last.
Part A and Part B.
Oh,
Sorry, yeah, what I meant was between Part A and Part B.
Maybe not.
Because the Part A looks so good that Part B, I was wondering.
Yeah, it looks the same.
It's 0.5 is the line.
Yeah, theirs is 0.5 everywhere. So I don't know if that's how it's supposed to be. So maybe I was wrong about this line. If it's here, it knows that it's fake, but here it's.
Yeah, because at that point, even your tail disappears. So now you can go up, but until, even if there's a little bit of data, it stays at 0.5, right? You see that where your cursor is, there's a little bit of blue there, which is, or a little bit of yellow still up to that point, and after that, it begins to slope up.
Okay.
But until that point, it's very close to 0.5, which is the desired. I mean, if your discriminator can't tell, then it will be at 0.5, right? So it can't tell eventually between fake and real until until after 0.75, to the right of 0.75.
Okay.
Because until that point, you still see yellow.
Okay.
There's still some real data there.
Okay. Yeah, and it's probably I was probably wrong that I think it should be all 0.5, because then the discriminator can't tell. Even if the data is from here, then it can't tell because there's still probability that that the data can be from there. Yeah, it's probably a misconception on my part. Okay. Okay, then sorry, I forgot to do that part, but let's go back to this one. So where was I? Yep, okay. Yeah, so this is the Cfr10 data set, and we're just gonna load it. And one of the first problem I encountered is this is a big data set. So just to go through one epoch takes 20 minutes or so, even longer. So it was very challenging to, but yeah, know if I'm doing anything right or wrong. So we'll use the Cfr10 architecture from the SN GAN paper, spectral norm. I don't know which part of the architecture he means. With Z, maybe this is the part. Z equals R128 means that the latent space has 128 variables, and Z comes from the normal distribution 0, 0, 1. I think this is meant to be identity at 128. So that probably means that each and every one of these Z are independent with mean 0 and standard deviation 1. That's maybe that's a fancy way of saying it. But here's the complication here is that or the main objective here is instead of upsampling via transpose convolutions and downsampling via pooling or striding, we'll use these depth space and space to depth methods for changing the spatial configuration of our hidden states. So the idea here is that we have a latent variable Z, right? And then this is 128 variable. So we have to make it bigger and bigger until it becomes 3 by 32 by 32 image for the generator. For the discriminator, we have to take a 3 by 32 by 32 and then turn it into a single value. And so in the not this paper, but this other, anyway, the other paper. So this is the spectral norm paper, a spectral normalization paper. But in the this paper, improved training by Wasserstein-Gahn, all of these are done. Where is it? I thought I saw, but all of them are done using. Am I? I thought it was here. Okay, all of them are done using the convolutions. So you make it bigger and smaller, all using convolutions. But in this one, I said no, we're not going to use convolution to make it make the size smaller. We're going to use these classes called depth to space and space to depth. So these two work pretty much right off the like how they give it works. So I can just go over it quickly. I'll just go over it here so that there's syntax highlighting. But it's just copied over here. So we have a block size, and this is the argument you give when you make a new depth of space, right? And then in the forward part of it, it's a neural network module, so you can chain it in a module. So the first thing is the positions are permuted here, and so I think this is where everything happens. So the expected input is 4 dimensions, right? As we expect. So the first one is the batch size, And if it's an image, you have the RGB color and then the width and the height, right? So that's 4 of them. So the first thing they do is they move the color to the back. So so then it becomes batch size, height, width, and then the depth, which is the color depth. Okay, and so, but that's just for the input. But you know, for the first input, after that, the depth, you know, after different layers, the depth just means depth. It becomes some 3D abstract 3D structure. So so we divide the depth attribute by the block size squared, and then we multiply the other two, the width and the height, by the block size, and then we reshape it, and then what do we do here? Split and stack.
It seems like we're reshaping it into a 5D rather than a 4D, right? Because there's this additional
No,
fourth, see the zeroth is batch size, then there is height, then there's width, and then there's a block size square before the depth.
Okay, and then it's split into 3 from the blocks T1 dot split self dot block size on the third dimension 0, 1, 2, 3. So it's reshaped and then split again, and then stacked. So they add the 5th dimension and then they chop it up from the 5th dimension, and then they stack it on top of the other, and then they reshape it back into the batch size, width, height, depth, and then they reshape it back into batch size, color, or depth, width, and height. Right, so yeah, so let me just run a quick thing here. So this is the test.
Yeah, is there anything where they describe in words what they're doing by that? It just seems like.
Yeah, it's just changing the shape of it and then moving things around. It's actually not making it bigger or smaller. So I think the idea here is that we have depth, and then this depth is increased to space. So here's a small example. So this is the starting point. Let's say 100 batch size, 64 is the depth, and then it's 100 by 100. And then if we look at the output, so where is it? Did I do input, comma output? So I should do output. But anyway, this is the output, right? So now it's 100 by 4 by 400 by 400. So the space was 4, so it takes 4 times 4, 16 off it, and then moves the 4 over here and moves the 4 over here, and then it just 4 is left, right? So this 64 becomes 32, and then this becomes 400, and then this wait, not 32. So 64 divided by 4 is what, 16, and then this becomes 400, and then 16 becomes 4, and then this becomes 400, right? So you can see the output. But that's just the input output. But then what they've done is they've like rearranged it. I think they've stacked it one on top of the other. They reshape it and then they stack it. So there's some other geometric stuff going on.
Yeah, I guess what they're trying to achieve is the equivalent to what the convolutional networks do, which is when you put it in the down, I mean, when you upsample, then it goes up, like in this case, meaning, you go from 100 by 100. Actually, no, the other way, meaning when you go in the generator, you increase the channels and reduce the, or is it the other way for the I think it's upsample for the generator and downsample for the discriminator, correct?
Yep. Yep.
So they're trying to achieve the same effect by doing it differently than using convolution network. I wonder, is this faster is the reason they do it this way, or I wonder why they do it this way versus
Yeah, I'm not sure. I think here, let me go to this one. This is the where did it go? Maybe it's here. Yeah. Okay, DCGAN tutorial. This is the one. So this is how they do it in the DCGAN, right? So you have 100 latent space, and then you use convolutions to make it bigger until it becomes a picture, right? So this is the generator. You have con transpose. The transpose is, I think that this is maybe that's what they're trying to do, is the transpose part of it, but they do also the other part. So
basically, the transpose would be, the upsampling, and the striding would be the downsampling. So in one case, you go up in when you upsample, and your and obviously the channels kind of either decrease or increase in inverse to, if your size is increasing, then the channels drop. If the size is decreasing, then the channels increase. That's kind of what you do in the conventional, like in a UNet.
Yep. But I think in this one, this step, the actual amount of stuff doesn't decrease or increase. It just changes the shape, right? And then it moves them around. The next step, the upsample and the downsample. Oh, sorry, the upsample and the downsample ones do that work. There's a upsample and downsample that changes actually the shape of it. So this one just like changes the shape. That one makes it smaller or bigger. So they have two different things. And so, okay, so let's go to the next one. Is that step to space, and then there's the space to depth. And I think it's similar, but then what happens is, instead of dividing the depth, it's multiplied by the box square size, and then the width and the height are divided. So it does the exact opposite of it, I think. But it looks like there's some other stuff going on here. So so it's being stacked without this thing being added, and there's double permutation. So yeah. I didn't do the, I probably should have maybe see how the matrix are changed. So I instead of making a rand one, I could make an actual specific one, and then it would see how they moved it around. I can. Okay, so but as you can see, if it's 16 by 16 by 16 by 16, you'll expect, if it's 4, then you get 4 over here and 4 over here, and so 16, and then you have 16 times 16, and this becomes this by 4 and 4. But yeah, I don't have the picture for how it's actually moved around. So I mean, I could make it, but yeah, we can go for. I mean, I could make a 4x4 matrix, but yeah, well, let's not do live coding then. We can go. Okay.
And then
So is the
I'm just
reason
curious
for
why
doing,
they would be implementing it this way. There ought to be some reason.
Okay.
Yeah.
So you were
yeah,
saying something, Arto?
Yeah. So is the reason for doing it this way to avoid this checkerboard artifacts? So you have when doing transposed convolutions, or is there something more to it?
I have no idea. So I think there's a reason they have to do the transpose convolution, and it's but in this paper, in this exercise, say, well, we're not going to do transpose, you're going to do this, and maybe it's like an actual implementation of how the transpose convolution works. I'm not sure what the answer is that.
Well, in transposed convolution, you will do the, like here, this reshaping and the computation, which is done by convolutions, are kind of disentangled. And in both cases, when you are upsampling and downsampling, it looks like the computation is done by regular convolutions.
Okay.
In both cases, right?
Yeah, I don't know.
Or in your code, I think you can find it in the code.
Oh,
So,
in this one?
No, in the implementation of upsample conv2d and
Okay.
downsample conv2d blocks.
Okay.
Yeah, so here you can see that in both cases we use regular convolutions. And transposed convolution, it's a bit different in terms of computation, and it has this checkerboard artifacts. I believe I briefly showed it when talking about this variational autoencoders. So basically, when you feed a random noise to a stack of transposed convolution, you will get out not a random noise, but there would be some checkerboard like pattern there. So I was wondering if doing it this way is the main reason to avoid this checkerboard artifacts, or maybe there is like more reason behind doing it, doing this space to depth and depth to space reshaping, and then doing the separate kind of computation step.
I don't know. So all he says is instead of upsampling by transpose convolutions and downsampling by pooling and striding, we'll use depth to space and space to depth for changing the spatial configuration of our hidden states, right? So, but it doesn't say why. Maybe it's in this paper, but
yeah, I see. Okay, yeah, fine.
Okay, sorry, I don't know. Okay, so the next one is the spatial upsampling with nearest neighbors, and then spatial downsampling with mean pooling. And then he gives a partial code, and so I try to make it into a module. Okay, upsample conv2d. So you can see it's so you take the input x. Okay, take the input x and you make four copies of it, and then you do depth to space. So I think it's related to how these do it, and then the block size is 2, and then you do a conv2d. So you have input dimensions, output dimensions, and then kernel size, stride. All of these come from the input. So it's pretty straightforward. So this class at least. So you have the depth to space and the convolution, and then you do the cat first, and then you depth to space, and then you do the convolution. Right. So, but the actual making it bigger or bigger is done here, but I don't know why it's nearest neighbors. So this X is something is being done to make 4 copies. I don't know if it's this part is doing the nearest neighbors, or is the DT depth to search is doing depth to space is doing the nearest neighbors. But okay, and so similarly, depth. What is it? Sorry, downsampling with spatial mean pooling. So it's it's a similar one. So you have space to depth, and then you sum it up. You chunk it into 4 parts. Chunk, I think, turns into a list of 4 little pieces, and then you sum it and you do 4, divide by 4, because we did 4. So this one made it 4 times bigger. This one makes it 4 times smaller. And then the block size is 2 here, because if the size that it changes is 2 times the block size here. So it's 5/4. So this matches up. But this makes sense why it's spatial mean pooling, because you're doing the mean and then you're averaging it, right? So this is a mean pooling, and then you do the convolution. So the way I implemented, this is all pretty straightforward, right? So it's the same thing. You do the space to depth first, then you chunk it, and then you sum it, and then you take the convolution. Yeah, this one, yeah. Okay, and then so we have another layer before we even go to the generator. So we have the ResNet block up. So we have ResNet block up, and then we also have the ResNet block down, but then we have to figure out what it is. So what does the ResNet block up do? There's X. So this goes through batch normalization, ReLU, Conv2D, batch normalization, ReLU, and the residual does the upsample Conv2D, and the shortcut just takes the original one and just does the upsample Conv2D, and then you return the residual versus the shortcut. So let's see if I think it's something I did it so that batch norm ReLU, conv batch norm ReLU, and then upsample, and then the shortcut just does the upsample part only. And I don't know why I changed the padding. Is it different? Padding 0, 1. Okay, that's I just copied over. And then you just, on the forward pass, you just do the residual and the shortcut. Right, so I think the ResNet part is the shortcut. The original data is added to the the network part, but there's still convolution going on in both cases. So okay, and then says ResNet block. This was ResNet block up. This was block down is similar. So, but without the batch norm. And so ReLU, Conv2D, ReLU, downsample, and then shortcut, and residual. That's my, that's how I think it goes. Okay, and then finally we get to the generator. So the generator is, okay, sorry, okay, generator. So the generator is Z, and then we have the take it from the normal and then the number of samples. So this is actually a sampling generator. Number of samples, and 128 is the latent space size. And so the first thing is that we take the 128 dimensional latent into a 4 by 256 space, and then we reshape it, and then ResNet block up, ResNet block up, ResNet block up, batch norm, ReLU, conv, and tanh. And then the discriminator has the same architecture except with ResNet block down and no batch norm. And this is discriminator generator. Yeah. So you do linear, and then you unflatten it to the right shape. Resonant block up, batch norm value conv 10H. And I think so. This so yeah, so conv2D, this is the number of input channels, this is the number of output channels, right? So it always so your input is 128 and the output is 3 by the shape of the whatever's left. And then so you have to have the right number of these things so that it produces a 32 by 32 image. So which should be fine, I think, because you have, this is fixed. 4 by 4 is fixed. And then you have yeah, so these are fixed, and I think all of these are carried over to become a 32 by 32. So so yeah, I mean it's just testing the shape. But if I have 100 by 1, so here I have the generator. If I give it a batch size of 100 and 128 values, then it should give me 103 by 32 by 32, right? So it kind of makes sense. And then where am I? And then so also the discriminator is the same, except that there's no batch norms. So so you do resonant block down. I did 5 of them, and then I can output it with dimension 1, and then I can flatten it, and then it become do tan H, or maybe I should do sigmoid here. Yeah. After this, like it falls apart for me. So yeah, it's just trying to get the shape right so that it can just output one single number. But we can look at the reference implementation. This is probably after this is it doesn't even work. Okay, so that's like the definition of the generator and the discriminator, which is dependent on this and this. So it's a very if I make a mistake anywhere, then it's going to be a headache to figure out. Okay. So it says the discriminator has the same architecture except with resonant block down and no batch norm, right? So we'll implement wGAN GP. So this is the wGAN GP, improved training of the Wasserstein GAN, and this is like the algorithm that I was trying to do. So this is, I can just go, let's go through it really quickly. So I think maybe it's useful. So we have the gradient penalty lambda, which is used here. So this is the regularization, or this is the what's the spectral norm part of it, right? So from the lecture, we have the norm of the gradient, and as we try to make it as close to 1, because if it's exactly 1, then it is the it has the Lipschitz property. So we have a regularization. So this acts like some sort of regularization. Then we have a lambda, and then so it's kind of like the gradient penalty, as if it's the regularization term. Okay, the number of critic iterations per generator iteration and critic. So it's just the same as before, number of times you train the critic. Batch size M. atom hyperparameters. Alpha is the learning rate, whereas atom here. Alpha is the learning rate, beta 1 and beta 2 are two more atom parameters that it takes. Okay, and then require initial parameters W naught. W naught is for the is it for the critic? Oh yeah, critic is W naught, and theta naught is the generator. So these are the neural network parameters, and so it's similar. So you have sample real data, sample random numbers. So we have the generated data, and we mix it with the random data, and there's an epsilon randomly chosen between 0 and 1, and our loss is this weird thing where we have the interpolated DW, and then the discrimination of the original data. We subtract it, and then we have the regularization, and then we do this for m iterations, and then after that we update the critic. And after we've done updating the critic, we we update the generator. So it's the same structure as this one, right? So let me go back to same as this one. We update the discriminator, and then after this we update the generator, but the equations are different. It should be the same idea, same way. And I think this is the same. This bottom part is the same. It's just this one. And maybe this is kind of similar. I don't know. I think this is supposed to be the main one for the spectral norm, right? That we have to be able to calculate the norm of the gradient of the discriminator and add it to the loss function. Okay, and then I try to make it exactly the same, and of course it's not. It doesn't work well at all. The first problem I had, which I didn't solve, is how do you get the gradient of? How do you get the norm of the gradient? So we have the model of the discriminator, and I went to all the parameters, and then I got the gradient. And then I took the norm of it, but this doesn't work because yeah, it's always 0 because the gradient is always none. So this part is not working. So that was the first challenge. That how do you do this? The second challenge is so even if I just ignore this part, the way they write this down is that the loss is accumulated over all of the batches, 1 to m batches, and then you update it over the sum of all the losses, right? So if I do it exactly the way they do it, where I accumulate all these loss functions and then take the gradient at one step from all of my batch data, I run out of memory. So yeah, this PyTorch exists out saying go buy more RAM. We've run out of RAM. So that doesn't work either. So there's like 2 problems, of course. And then even if I cheat and say, okay, I'll just optimize it in this loop. So this is a mess, but you can see, yeah, there's still more problems that it. Some of these shapes aren't right, or the way the data samples aren't right. So, but I was just trying to make it exactly the same as same example, but we can just look at the reference implementation for this one, and rather than rather than mine. Okay, so depth to spacing is exactly the same. And so downsample con2D is the same, right? So spatial depth chunk. Oh yeah, this similar one. I think I looked at it and it's the same. So ResNet block up is yeah, I probably I don't know what the self.layers is, and it's only one of them. So
It is building up the module, right? It's just the list. It's a module list. So, and then of
oh, okay.
batch norm value, con2D batch norm, blah, blah, blah. And then that's what the self.layers is. And then you reproduce the number of them.
Okay. Oh, I see. I see. Yeah, it's just going through this and then doing this much
Right.
for the first one and doing the last one, and then adding them up. Okay. Yeah, it's okay. It's it's a so instead of sequential, it's a module list. Okay, I see. That makes sense. It's a nice another trick to use. Okay.
No,
And
actually, the
Yeah,
way
they
you
have
do
these
it
things
is
of module
cleaner.
dict and module list and stuff. Right.
In this case, there is no reason to use a module list. It could be it is useful when you have like extra inputs to the layer. Then you cannot use sequential, and then it could be useful. But in this case, I would say that your implementation using sequentials is kind of cleaner. But yeah, the computations are the same, so no essential difference here.
okay. And it's the same one here for the ResNet block down. Does the first 4 and then the last one. Okay, and then for res block, so yeah, I think maybe I made a mistake here because it says it adds the raw input to the X. And then it goes through all of the module list for the other X up. Res block. What is, did we make a res block? I don't remember. There was a res block down and a res block up, but I don't know what this res block is. Okay, and then we have the generator. So we have the linear part, and then we have the res block up, 3 res block up, batch norm value conv tan h, and okay, yeah, it's just here. Okay, I just put it into sequential, this network, and then noise is. Oh, okay, this is for sampling down the road. Okay. And here, they do the fully connected layer, they reshape it, and then they send it to the network. I just used, yeah, I use that thing, yeah, the reshape, the unflatten that does the reshape. So that's the only difference. But I think this one, they do something different here. So in the discriminator, they have only 2 ResNet block down, and then they use this res block. So, and and to make it into the correct size, they use the sum. They sum up this dimension 2 and 3 and squash it into 1. Instead of doing a whole bunch of ResNet block down, they just do the res block and then they just squish it down by doing a sum. And then they send it to the fully connected layer. Or wait. Oh yeah, and then they send it to the fully connected layer and something outputs. Oh no, sorry, this is, so there's 2 of these, right? So this is the one, 128 by 1. So you have 128 and then you get the 1 value back. So it still produces a 1. 1 output, right? So the discriminator also produces 1, but when I did it, I thought we had to use the ResNet block down all the way, but use a different stuff. Okay, so that's the difference. And then we can go over the training code, and it is much more complicated. Okay, so here, this is all the parameters, right? So number of critic iterations. This is log interval to save the model, I think. Batch size, number of filters. This is for the data, batches in epochs, number of epochs, and current iteration. So it's the same, the generator, make the optimizer, and make the scheduler. So this is pretty straightforward, and this is for the data loader. Okay, so the main thing is in the training. So the problem I had was the gradient penalty. How do you take care of the gradient penalty here? And so this is something I haven't seen before. So you can get the gradients by doing torch autograd.grad. So you have this is your output you want. This is your input, which is this value. And yeah, and I don't know how they do it, but essentially this gradient penalty is how they calculate the gradient penalty, and then this is the loss function. You can just add the fake data minus the equation is slightly different. So right, so discriminator of the fake data, discriminator of the real data times 10 is the lambda. Lambda is 10. This is supposed to be lambda, and then the gradient penalty, right? So this equation is slightly different from the paper. Paper of you take this one and then you take the x. Oh no, sorry. Maybe I read it wrong. So the x tilde part is only used for the gradient. So this is the real data. Okay, that's the right equation. Okay, so it's the real data, and this is this is the fake data. This is the real data, and then you take the gradient of that of this epsilon random point between the real and the fake data, and then you find the gradient. So this requires the using the torch autograd. So you calculate it, the real data and the fake data, and then you have to send it to interpolated is the input, output is this one, and then I don't know where the grad part comes, the discriminator. Yeah, okay, D output is the self.d interpolated. So this is the discriminator interpolated. So, and this one does the gradient calculation independent of doing the independent of the training and all of these backwards stuff, which makes sense, right? So we have to calculate this gradient for x hat and for discriminator. But yep, so yeah, and then the gradients probably come in a nice one-dimensional vector, outputs ones, input size, output dot size. So yeah, that part is taken care of. So, and then yep, this is a gradient norm. So instead of doing norm, they have the square root and then the square sum of the square root, sum of the squares of the gradients, and then take the square root and then subtract it and then do the square and then do the mean over all of the different batches. Okay, so that part, like how do you calculate the gradient? So I think this is the main function, and I didn't know about it. Okay, right. So the second question, the second thing that I had was that what is this? How do you accumulate all of the LIs? Like what does it mean to accumulate it and then take the W off it? And unfortunately, I think they so they don't accumulate it. This one, they have the GP, there's the loss, and then this is done backwards right away for each of the batches.
There in the algorithm in the paper just writes it like in the for loop. Yep. But what it actually is, so in the code it is done in a batch form, you know. So that's just we iterate here in the gradient, the third loop or the second for loop, that one over I. From 1 to m, we just iterate over the batch, right? But in like on practice, what we do, we just do this in a batch form. You can write essentially all the computations we do in this iterative form, and then you see like it is average over the batch. Or you can do here, you actually do this computation over all batch, and that's the same mathematically, you know.
Okay. Okay, that's I thought this would be equivalent, but if I do it this way, where I try to, you know, I take loss d0 and then I sum it all up, then it runs out of memory because I think it's making a very, very complicated graph, and it just runs out of memory. But in this case, I think taking the sum of it and taking the average of it, it's the same operation, but it doesn't. It works, right? So yeah, and so I think that's all there is, and so some of the results are here. And then when I try to run it, of course, just going through one batch takes about 10-20 minutes on the CPU. So I have to turn this into a GPU code and then make sure everything is right. So one of the things I was trying to do was to just train on the first 500 ones, and then, you know, over completely it will overfit this data, right? And it would probably learn the images and see if I can just make it work or not. But it wasn't even working for just taking the 500, because if I take the whole 20,000, I think it's 20,000. It doesn't say. And train is, I think, 20,000. So it takes about 10-15 minutes just to go through all of this. So I was trying to just see if I can make it go through just this much, overfit it at least, and then give me some data to make sure that the pipeline is working. But obviously my gradient calculation isn't working, and then this was causing overflow. So this is all a big mess here. So this is the reference solution, and I think this is the right way of going about it. And this is the same trick of using the mod number critic so that it's all this loop is in the same loop, right? So all of this is in the same loop. Oh wait, all of this is in the same for loop instead of having two different for loops in here. Okay, and yeah, and so I'll try to get my code working, and then we can go next week. Then we can go into this ByGAN, and the idea here is that so we have a generator and a discriminator, and we also want to train an encoder, so that if you give a real image, you can also get the latent code Z. So instead of just having a generator that gives you have a latent code and it produces image, we also have a encoder that if you give it an image, it can give you the codes. So we can do that next week, and the rest of the oops, sorry, this one. Where did it go? Yeah, the rest of the collab. And the collab has this part, different KL divergences, differences between KL and the Jensen-Shannon inequality. Reverse KL, Jensen-Shannon divergence. And this is the non-saturating that we already, it produces the graphs for it. And this is the homework one. And question number 4 is homework number 2. And then this is inception score evaluation. And Frechet inception distance. And then this will be ByGAN again. And then that's the end of the that. And then we can wrap up the this, and then that'd be the plan for next week. Any questions or any discussions we want to do?
Just a comment. I think
Sure.
Back what Arta was saying, it seems correct because I just did some poking around, and it looks like TensorFlow has this modules of depth to whatever shape and shape to depth, and they seem to have to do with the thing that I think Jeremy in one of his lectures goes through in great detail when he talks about UNIT, which is how to get back very good high quality sample or video super resolution using sub-pixel convolutional networks, and this depth to size or depth to shape or whatever, and the reverse of it is essentially applying pixel shuffle or and so Arto's intuition or his comment about it trying to avoid checkerboard artifacts is indeed correct, but it actually does it through a different way of implementing sub-pixel super resolution. So there are some related posts or Stack Overflow Q&A that I'll just post to Slack later, but that seems to be why they're doing it. I mean, it doesn't exist in PyTorch, but apparently it exists in TensorFlow, so they have implemented that in PyTorch.
Okay.
That's what it is.
Oh, thanks. Cool.
Great. Thank you. Okay. Yeah. If there isn't anything else, then we can end early. Then I'll try to do the rest of the remaining stuff next week, and we can finish up with the GAN.
Great. Thanks, Mochen.
Okay, thank you.
Okay.
That stuff with gradients is definitely an elaborated code, and it's kind of tricky to make it work. So yeah, good job.
Okay, thank you. Yeah, I was trying to make it a separate test so that I could play around and figure out how just getting the gradient part and working. So because I've never seen it before. Yeah, and so that was very strange. Okay, and yeah, it was overflowing the memory and all that stuff. So it's a big mess of code that I did. So I'm still not very good with PyTorch yet, but I'm improving. So okay, well, thank you everyone. We'll see you next week.